Hey guys, what's up? Hopefully everybody can get in today. Gonna wait for a few more people to get here. Don't have to start right away. Basically just gonna pick up where we left off. Last time. I'm gonna wait for everybody to get here though. Still lacking about 13 people. So we'll wait just a few more minutes for everybody to get here. Hopefully they'll get here soon. So I'm just going to mute everybody to start with, and then if you have a question, you feel free to unmute yourself, ask a question, or I'll just try to have the chat open up on the side, and you can chat or ask a question through the chat as well if you don't have like a microphone or whatever it is. So I'll kind of do it like this here, have the chat on one side, and then I'll just write over here on the other side. So again, I just want to make sure everybody gets in. I have the meeting room open, so or the waiting room. Sorry. So the waiting room forces you to wait before you get in. Anyway, anybody not here, we're pretty much good to go. They can just watch it later, I suppose. So if people show up in the waiting room, they can't get in, just let me know in the chat. I'm just going to get started. So you can't see the chat window? Okay, yeah, that makes sense. But I can see the chat window, so if you ask a question, I will respond. So, all right, cool. So I guess for you, it looks like the screen is just like, or the OneNote document is just over here, and it's like, why do you have it over there if you can't see my chat? But yeah, so let's get started. Linear and exact equations. So we kind of started linear equations last time. Let's do some recap and then some examples. So a recap of linear equations. So recap linear equations, linear first order, differential equations. So to recap, we had, let's say, in standard form, we had y prime plus p of x, y equals f of x. Yeah, I think it just happened like back in the fall. They made that an option for OneNote. So that's pretty cool. Whenever you print it, though, it goes to white paper, though, and changes the ink to black. So first order linear differential equations, y prime plus p of x, y equals f of x. So we said to solve a linear equation, the first thing we do is we compute the integrating factor. So we compute integrating factor, and that's e to the integral p of x dx. Step 2, multiply the whole equation by the integrating factor. Step 3, undo the product rule. Step 4, integrate both sides with respect to x. So integrate both sides with respect to x. Number 5, don't forget plus c. And number 6, solve for y. And number 7, use any initial condition to solve for c. So this is basically the steps we're going to take to solve a linear equation. And yeah, let's just look at some examples here. So we have an example. Solve the initial value problem. So solve the IVP, initial value problem. And we're going to have a differential equation and an initial condition. So the differential equation is y prime minus 3y equals, or sorry, minus e to the x equals 0, and y of 0 equals 3. So we want to solve this initial value problem. The way we're going to do that is use the method of the integrating factor, because this is a linear differential equation. However, it's not separable. So I actually have to use this method because it's not a separable equation. So what we do is put it in standard form. So in standard form, we have the equation y prime minus 3y equals e to the x. So that's our equation in standard form. Now, first we want to get the integrating factor. So the integrating factor is going to be e to the integral 3, negative 3 dx. So e to the integral negative 3 dx, which is going to be e to the negative 3x. So that is our integrating factor. Now you might ask yourself, why don't we put a plus c here? I'll talk about that in a little bit when we actually do get a plus c. But just don't worry about a plus c when you're doing your integrating factor. Only when you're doing the integration in step 4. Don't do it in step 1. So this is our integrating factor. Now multiply the whole equation by the integrating factor. So now multiply the entire equation by e to the negative 3x. So that's going to get e to the negative 3x y prime minus 3 e to the negative 3x y equals, see, e to the negative 3x times e to the x. Okay. Now undo the product rule. On the left, you should always see d by dx of your integrating factor times y. On the right, we'd add those exponents together, we get e to the negative 2x. So do the undo the product rule on the left. So now we're going to integrate both sides with respect to x. So integrate with respect to x. On the left, integral and derivative cancel. That's just e to the negative 3x times y equals negative 1/2 e to the negative 2x plus c. Okay. How do we get the integrating factor? We get the integrating factor by integrating, let's see, e to the integral p of x dx, where p of x is whatever's multiplied by y. In this case, y is multiplied by -3. So we integrate do e to the integral -3 dx. Unless your question is, how do we get the integrating factor in general? Like, where did that come from? Which we discussed last time. So, did I answer your question, EJ? You said, how did we get the integrating factor? Okay, cool. All right, so now we're almost there. We've got to solve for y. So now just basically multiply both sides by e to the positive 3x. So we get negative 1/2 e to the x plus c e to the 3x. So we've got a pretty good start on this problem. So that's y. Now we want to solve for c by plugging in our initial condition. And what was our initial condition? Our initial condition was y of 0 equals 3. So now use our initial condition to solve for the constant. So 3 should be equal to negative 1/2 e to the 0 plus c e to the 0. So 3 equals negative 1/2 plus c. So that would tell me that c equals 3 plus 1/2, which is 7/2. So y of x is equal to negative 1/2 e to the x plus 7/2 e to the 3x. And that is the solution of our initial value problem. Now, that's a unique solution because we have an initial condition here and the function doesn't have any singular points as far as we're concerned. So, good to go. Good to go on that one. Any questions? Just type them in the chat or unmute yourself. Oh yeah, this is being recorded. So if you don't want to be recorded, leave the chat or leave the meeting and just watch it later. So any questions? We talked about this last time. Let's see, go over the left side of the equation on undoing the product rule. Yeah, so there's like two ways to think about undoing the product rule. You could either say, so undoing the product rule, d by dx of e to the negative 3xy will be equal to e to the negative 3xy prime minus 3 e to the negative 3x times y. So it's just kind of seeing it. That's the first way. You could say that you either see it directly. Okay, I'll come to that in a second, Ben. So you could either just see that the product rule here goes back to this, or actually every time it's always going to be d by dx of integrating factor times y. Always. So this is always what we get when we undo the product rule. So if you take d by dx of integrating factor, is it always the same as the integrating factor? No. Here, integrating factor is e to the negative 3x, and d by dx of integrating factor would be negative 3 e to the negative 3x. Ben asked, why can't, he said basically right here, why does that not just become its own constant? Well, it doesn't become a constant because there's an x. So if there's an x, it's not a constant. So you can't just absorb it into the plus c. Okay, does that make sense? Yeah, exactly, because it has an x. Okay, cool. First example, that's good. All right, let's look at another example. Let's see. Actually, definition. Start with the definition here first. The definition is of a transient term. So definition, a homogeneous solution. We'll call it y sub c, is said to be a transient term Whoa, losing my mind here. The writing. Transient term, if y sub c approaches 0 as x goes to infinity. So if we think about our last solution, neither one of those are transient terms. Like there's no transient term in our last solution because those go to infinity as x goes to infinity. So that is not a transient solution. There's, or at least we could say there's no transient part to our solution. So, just check one thing here. Make sure I'm using the right microphone. I keep leaning over to my Yeti and I'll make sure I'm using it. Okay, cool. So that's what we mean by a transient term, a term that goes to 0 as the variable goes to infinity. Let's look at another example here. Let's see, I don't want to do that one. Let's do this example. Got an example. It's just not an initial value problem, so we're not going to solve for the plus c. But the differential equation is y prime plus 1 over xy equals sine of x. So let's look at the solution to this one. It's going to just have a different integrating factor, which means it's going to be different overall. It's already in standard form. We don't really have to do much there. We just identify p of x, which is 1 over x. And so the integrating factor is the e to the integral 1 over x dx, which is e to the natural log x, which is just x. So that's pretty straightforward there. That's a really nice integrating factor. So then multiply through by the integrating factor. So now multiply by integrating factor. So multiply the whole equation. So we get x y prime plus y equals x sine x. Okay, and now undo the product rule. So that's going to be d by dx of x times y equals x sine x. Again, just verify that if you take this product rule, you go back to what you had before. D by dx, you get y prime times x plus 1 times y. And that's what we have. It's always integrating factor times the dependent variable to undo the product rule there. So now integrate both sides with respect to x. So integrate both sides with respect to x. On the right, we're going to have to do integration by parts. On the left, we just get x times y. So u equals x. I could just do a tabular integration here. Put a u and a dv column. So tabular integration. I'm going to use this a lot later in the class when we go through Laplace transforms. But x, 1, 0. So I just differentiate this thing to 0. And then over here, I integrate this thing. So negative cosine and then negative sine. And then I attach them diagonally, put a plus sign here, a minus sign here. And then I wouldn't need to attach this because it's 0, so that doesn't do anything. So this is going to be negative x cosine x. Minus minus will be plus sine x plus c. So that is what the integral is. If you do that integration by parts, you can do it the old-fashioned way, that's fine. You get the same thing, of course. Now, solve for y. So y equals, divide everything by x, basically. So it's going to be negative cosine x plus 1 over x sine x plus c over x. And that's pretty much as far as we can go because we don't have an initial condition. Particularly, we wouldn't even need one at 0. We'd need one somewhere else because we can't have x equals 0 in the solution because that was basically a singular point of the differential equation already. So does that one fly? Is that good? Questions? Since you guys are pretty active in the chat over here, we may switch to doing like a YouTube live thing, and that might work out a little better instead of doing the Zoom stuff. Let's see. Yeah, maybe we'll see. All right, another example here. Let's see. Oops, sorry, hit my microphone. It's kind of stuff you can't do on YouTube Live. Oh, gross. This one's awful. Let's do it. Example. How do you do the tabular thing? Sweet. Yeah. Let's see. Best way to start a problem is hit the microphone. Let's see. How do you do the tabular integration thing? Well, basically, what you would normally let u be, you stick right here in the u column. And if it's a polynomial, it's going to differentiate down to 0. So what you do in that u column is differentiate until you get to 0. In the dv column, you integrate until you get to the same level as your 0 on your left. And then what you do is you multiply these two terms, like u times v minus integral v du. So that's why that minus sign is right here, but then you integrate that and you get negative sine x again. So it's really just like doing the integration by parts, like quickly without, we'll look up a video, I guess, if you want to go into more detail of how to do, of how to do tabular integration. So you just Google that. It's a good way, especially if you have a polynomial on your function, like polynomial times cosine or polynomial times e to the x. It's definitely the fastest way to do it. And we're going to do that a lot later. Yeah, I got the chat on. Sorry. Yeah, I got the chat so I can see what you guys are typing. If we did like YouTube Live, I could see the chat regardless of, you know, whatever's going on. But with Zoom, I just have to pull it off to the side for now. So you guys can't see it, but yeah, I can see what you're saying. So yeah, not shameless. It's completely shameless. Not shameless would be shameful, right? Sorry. Yeah, I was thinking about just emailing every school in the United States and tell them, just kidding. Let's look at another example here. This one's gross. Like I said, best way to start it, that's right. So y prime plus y equals cosine x. So let's look at it. Solution. It's going to be, let's see, p of x is just 1. So the integrating factor is going to be e to the integral of 1 dx, which is just e to the x. So you can already see why this is going to be gross, because I'm basically going to multiply everything by e to the x, which means I'm going to multiply cosine by e to the x, and I've got to integrate e to the x cosine x. So we get d by dx of e to the xy equals e to the x cosine x. So I just kind of do it all in one step. You know, the more comfortable I get with the process, you multiply the whole equation. It's always going to become d by dx of integrating factor times y, and then basically the right-hand side multiplied by your integrating factor. All right, so now we integrate both sides with respect to x. On the left, we just get e to the x y. On the right, we have integral of e to the x cosine x dx, and that one we know is integration by parts twice. So now this one, we have to integrate by parts twice. Let's see, I can use tabular to do that, but that may be a little confusing if you don't understand tabular. So we'll just do this one the old-fashioned way. Let's see, let's see, that looks like a spray brush. We'll not use that. We'll do u equals e to the x. Let's see, what do I want to... I'd actually rather integrate e to the x and differentiate cosine. So let's say u equals cosine, and dv equals e to the x dx. So du be equal to, let's see, derivative of cosine is negative sine dx, v is e to the x. So this is going to be, let's see, e to the x. Let's see, how do you do this? You say integral e to the x cosine x dx equals e to the x cosine minus will be plus integral e to the x sine dx. And now I do integration by parts again. So that's u equals sine dv equals e to the x dx, du equals cosine dx, and v equals e to the x. So it's going to be e to the x cosine x plus, and then e to the x sine x minus integral e to the x cosine x dx. And that's integral of e to the x cosine x dx. And now we have integral e to the x cosine x on both sides. So I can move a 2 over here. 2 times integral e to the x cosine x dx equals e to the x cosine plus e to the x sine, which means this integral e to the x cosine is 1/2, or I could say e to the x over 2 multiplied by cosine x plus sine x. So this is going to be e to the x over 2 cosine x plus sine x plus c. So that's a throwback to Calc 2, just doing some serious integration by parts to get that integral e to the x cosine x. Just hang in there with it. Don't give up on it. You got it. Now solve for y. So y of x will be, basically divide both sides by e to the x. So we just get 1/2 times cosine x plus sine x plus c e to the negative x. And that's our solution. Explicit solution. However, we have no initial conditions, so we can't solve for the constant. So just leave it like that. So any questions? That pretty much wraps up our discussion about linear equations. I'll post some more videos online, just some more examples that you can look through, maybe some harder stuff, harder integrals, things like that, just to get you some more exposure. Any questions? Just take a second. Hey, you're going to have to integrate by parts on the test. Possibly, probably. Know how to do it. I don't think we'll ask you to do it twice, but maybe. I mean, maybe. Anything's fair game now, I think. Yeah, this was basically the example part of the section we were going over, 2.3. So just doing some examples after we had derived the integrating factor approach last time, or at least kind of showed where it comes from. So yeah, this is basically the end of 2.3, linear equations, linear differential equations, first order. Yeah, definitely know how to do integration by parts on the exam. Speaking of the test being conducted the same way, or is that changing? So definitely still working on that. Dr. Ming and I had some discussion yesterday about what we're going to do, and we're still working on it, but I'll tell you some more maybe at the end of class of like the next steps we're going to take to try to get some stuff going. But yeah, that sounds illegal, and like I'll lose my job. As Jonathan says, we should have a secret in-person meeting. So, actually, that was one of my proposals was basically just show up for one day. Like 30, 40 people in a room for one day wouldn't be that bad. But they were like, nope, just can't do it. Even like I have a class with 12 people in it. On Monday, Wednesday, Friday, I was like, well, that's just like 12 people. And so they were like, still, you can't have class. And I'm like, man. So yeah, I've been trying to work it, but it's not working. I didn't say anything about cookies this quarter, so you you can't get any cookies this quarter. At least I'm not promising anything. Man, you guys are like ruthless. I say one thing about cookies in like every freaking class. You're like, where are my cookies? So I love that like we still can banter even online. I'm just reading like your comments and stuff. Oh, I think only super small research labs are meeting. Yeah. Thanks, Sam. Glad you like the cookies. Thanks, CJ. Maybe I can make some digital cookies. Yeah, actually, as soon as you log into Zoom, I'm tracking all your information. So yeah, we already got all your cookies. I'm getting cookies from you, basically. Thanks for the cookies. Yeah, you're welcome. Okay, 2.4. So let's do some more stuff. This is great. Yeah, you guys are the first class to like actually interact through the chat, like seriously interact. So it's good stuff. I'm enjoying it. Definitely makes it a little bit more bearable. It's kind of tough whenever people are just like sitting there. Maybe one person will say one thing. But it's good stuff. So let's look at 2.4. So 2.4 is all about exact equations. 2.4, we call it exact differential equations. Let's see. Definition. see. Well, I guess I don't want to define it. I want to derive it first. So let's derive it. So the setup is as follows. Consider z equals f of xy. So it's a function of two variables, z, it's really just a surface if you want to call it that. So z is a function of x and y with continuous first partial derivatives. So with continuous first order partial derivatives. In a, let's say it says in a rectangle R in the xy plane. So that's our setup. We just have a surface or a function of two variables in the xy plane. Then from Calc 4, or calculus, the total differential, or just differential, dz. Man, anybody remember what that was? So that was a long time ago. It's back in the winter. That was partial f partial x times dx plus partial f partial y times dy. So that was the total differential. Now suppose that f of xy is equal to a constant. For example, like an implicit solution to a differential equation. So if f of xy is equal to a constant, then that change in z is 0. So basically, z is a constant, which would mean dz would be 0. There's no change in z because z is a constant. So then that would tell us that the partial f partial x dx plus partial f partial y dy equals 0. And that is basically going to represent a differential equation for us. So if we let m be equal to partial f partial x and n be equal to partial f partial y, then we would get a differential equation m times dx plus n times dy equals 0. And you could like rewrite it as dy dx equals something, but this is just like splitting up the differentials and writing it as a differential equation this way. This is truly a differential equation. Like differentials are literally broken up in this equation. So this is a differential equation at the very heart of the definition of differential. So now we say that it's an exact equation if certain conditions apply. So definition. The differential equation, we'll call it dE, of the form m of xy dx plus n of xy dy equals 0 is exact in a rectangle R if there is a function f of xy such that partial f partial x equals m and partial f partial y equals n. So that is called an exact equation if there is a function little f of x and y, such that you can take the partial and get m, take the partial with respect to x to get m, and a partial with respect to y to get n. Now, if you remember from calculus, this feels very much like a conservative vector field. So it's basically like finding a potential function for a conservative vector field. If there exists a little function, or a function little f, then the field was conservative. Well, now, basically, if there exists a function little f, such that partial f partial x equals m and partial f partial y equals n, then we say the differential equation is exact. Well, by Kleros Theorem, the differential equation m dx plus n dy equals 0 is exact. Let's see, is exact if partial m partial y equals partial n partial x. So that's a test for exactness. That's our test for exactness. So we can figure out whether or not a differential equation is exact if these are satisfied. If they are satisfied, then we can find the function little f of x and y, set it equal to a constant, and get an implicit solution. So the solution, the steps for solution, number one would be test for exactness. So test exactness. Number two, find little f of x and y. So find potential function. Number three, set f of x, y equal to a constant. And four, use initial condition to solve for C. If it's not exact, we could make it exact, possibly, but it requires some more discussion, and we may go through that. We probably won't go through it today. I may make like a separate video on that, of how to derive the multiplier, basically another integrating factor type thing. But we can make something exact possibly if it's not exact. So let's look at an example here. So example, show that y prime equal to secant squared x minus 2xy over x squared plus 2y with initial condition y of pi equals 1 is exact, and solve. So basically what we need to do first is rewrite it as dy dx equals secant squared x minus 2xy over x squared plus 2y. Now basically what we're going to do from here is cross multiply everything to split it up into the differential form. So split into differential form. And the way we do that is basically just cross multiply the terms. So we'll get x squared plus 2y dy equals secant squared x minus 2xy dx. And now all that's left to do is move, we'll say move one side over to the other. So now move everything to one side. I'll move the dy, I guess. So we'll say secant squared x minus 2xy dx minus x squared plus 2y dy equals 0. So just move the dy, make it negative. Now identify m and x. So now m is whatever is multiplied by dx, and n is whatever is multiplied by dy. So now test for exactness. So test for exactness. And what we need to do is take partial m, partial y, which is negative 2x, and partial n, partial x, which is negative 2x as well. The n includes this negative sign. So just be careful. So the n includes the negative sign. So this implies DE is exact. And we can solve, basically find a potential function. So f of xy equals the integral of m dx, which is going to be integral of secant squared x minus 2xy dx, which is going to be tangent x minus x squared y. And our assumption was that that's equal to a constant, so we'll move the constant over to the right-hand side. Oh, well, let me say plus g of y, maybe something that only depends on y. And again, we set that equal to a constant. That's our assumption, is that the function, if it does exist, would be equal to a constant. So we got tan x minus x squared y plus maybe some function that only depends on y. Set that equal to a constant. That's f of xy, but let's also do f of xy equals integral of n dy. It's going to be integral of negative x squared minus 2x, or sorry, minus 2y dy. It's going to be negative x squared y minus y squared equals, or plus h of x, we'll call it, plus h of x equals a constant. So then we take the union of these two, and I say, okay, h of x must be tangent of x, and g of y must be negative y squared. So then overall, the function is going to be tan x minus x squared y minus y squared equals some constant. So this is our implicit solution, but we can find the constant c because we have an initial condition, y of pi equals 1. So y of pi equals 1 means when x equals pi, y equals 1. So plug those values in over here and solve for the constant. So tangent of pi minus pi squared times 1 minus 1 squared equals c. So that tells me that c is going to be, see, tangent pi is 0, so negative 1 minus pi squared. So weird number, but not too crazy. So we substitute that in. Okay. Our solution, implicit solution, would be tan x minus x squared y minus y squared. I can move it all to the left and say plus 1 plus pi squared equals 0. So that would be an implicit solution to the differential equation. So this is an implicit solution because I'm not solving for y. It would be difficult here to solve for y. I mean, I could try to use a quadratic formula, but that doesn't sound good. So just leave it as an implicit solution. Notice there's another implicit solution, which basically you could multiply everything by -1 on both sides and it's still the same equation. That's another implicit solution. So either one is technically okay. I think on your homework it accepts one but not the other. I think we tried to fix that so it would accept both. So, but just be careful. If you were to multiply this equation by -1 on both sides, it would still be a solution. Any questions? So it's similar to the potential, yeah, from calculus. When you find the potential function of the vector field, it's the same process here. It's just you have to remember like what are the functions that you have to integrate, and you have to integrate m with respect to x, and you have to integrate n with respect to y. So, but yeah, it's similar. And now we have a C that we can solve for if we have an initial condition. So that's a good one. It's a good method. I think I keep zooming out and it keeps getting bigger on me. My writing is going to be very large. See if I zoom out. Yeah, you can see it's starting to grow. So I'm trying to hone it back in. So I keep zooming out, and as I zoom out, I keep going to the edge. As I go to the edge, I keep zooming out. So it's like, gotta stop it. Gotta start bringing it back in. All right, so let's look at this example. It says solve the differential equation here, and it is the equation 1 plus 3x squared sine y dx plus x cubed cosine y dy equals 0. So basically just going to use the integrating factor to solve. So the solution, I guess it's just good. Sorry, we're not going to use the integrating factor. We're going to use the potential function. We should identify m, we should identify n, and test for exactness. It's already in differential form, so we don't have to do any algebra up front. So first, test for exactness. So test for exactness. So let's see, what do we have here? We have m, and here we have n. So partial m, partial y is going to be, let's see, that's going to be 3x squared cosine y. And partial n, partial x is going to be, sorry, yeah, that's right, cosine y. And differentiate this with respect to x, we get 3x squared cosine y. So we're good to go. It is exact. Those are the same. So now integrate m with respect to x. So f of xy is equal to the integral of m dx, which is the integral of 1 plus 3x squared sine y dx, which is x plus x cubed sine y plus maybe something that only depends on y. So let's say g of y equals a constant. And then f of xy equals integral of n dy, which is integral of x cubed cosine y dy. Integrate that with respect to y, we get x cubed sine y, plus h of x, maybe something that only depends on x, equals a constant. So then take the union, we get f of xy equals, it's going to be x plus x cubed sine y equals a constant. And there's no initial condition here, so this is our implicit solution. Whoops, our implicit solution here. So sweet. That's a good one. Pretty easy, not too tough on the integration there. So that's always good. Just to kind of get our feet wet, get the idea down before we get into some tougher stuff. So any questions so far? What do we do if they aren't exact? Well, I'll do something separately on that. We're not going to cover that because we don't have any problems like that in the homework, and we don't have anything like that on the exam. But I'll cover it in like a separate video. I'll post it on my channel, and you can check it out. But just in case you want to see, I'm not going to cover it right now. Other questions? Okay, cool. We are flying through this stuff. I guess it's easier to just kind of write without like walking back and forth across the board and erasing, and it's easier to fly through stuff. So I don't want to like blow you away with material. I mean, sure, I do want to blow you away, but I don't want to just leave you behind. I'm always about blowing your mind, but I don't want to leave you behind. It's a good catchphrase. So we'll go into the next section. Because, I mean, these are very similar to what we did in calculus. There's not much difference. You've kind of seen this before. Now all that's different is maybe you have an initial condition. You can solve for the constant. Not a big deal. So 2.5. is solutions by substitution. And what we're going to do here is we're going to talk about homogeneous equations, Bernoulli equations, and then general substitutions. So the first thing is called homogeneous equations. The second thing is Bernoulli differential equations. And then the third one is general substitutions. So that's what we're going to do now. Let's take a couple of minutes break. I'll pause, and you can take a few minutes yourself, decompress, digest, do all this stuff. I'll be right back. Let's see. Christopher posted something that I cannot see. It's just an empty box. That's sad. Oh well. It's a mosquito. That's so sad. Let's see. Homogeneous equations. The first thing, there's going to be 3 different types of equations in this section, and knowing how to use each method is important, and knowing when to use each method is important. So when you get to the final exam, and couple of months, you're going to be like, man, what do I do here for this differential equation? It's kind of like integration. You're like, what is my strategy? How do I solve this equation? So you should see an equation and know what method to use to solve it, basically. So that's really going to help in this section. We're going to have 3 different types of equations. They're all pretty distinct. You can kind of tell what to do. But the first one looks kind of similar to exact equations. So that's the only thing you don't want to do, is confuse the first thing that we do here with exact equations. But for the most part, it's pretty straightforward. If it's not exact, then we're pretty much going to do this, because I already told you that you're not going to have to make it exact. So that's kind of why we do that. But yeah, the first one is called homogeneous equations. So number 1 is homogeneous equations. So that's the first thing we're going to do here, homogeneous equations. The first thing we need to do is define how a function is homogeneous. So definition. What do we mean by a homogeneous function? So if a function f possesses the property f of t times x comma t times y equals t to the alpha times f of xy, then, or I should say for some real number t, then f is called a homogeneous function. So basically, if you plug tx and ty in place of x and y, and you can factor out t to some power from that function, basically, then we call that function homogeneous. For example, just look at a quick example to show what we mean. F of xy equals x squared y plus y squared x is homogeneous of degree 3. So if we say of degree 3, we really just mean that we can take out t cubed from the function when we substitute that in. So let's see how that works. So f of tx comma ty be equal to tx quantity squared times ty plus ty quantity squared times tx, which would be t squared x squared ty plus t squared y squared times tx. And we can rewrite that as t cubed times x squared y plus y squared x, which is really t cubed times f of xy. That means the function is homogeneous of degree 3. So that's what we mean by a homogeneous function. Now, we use this in the definition of a homogeneous differential equation to define homogeneous differential equations. So, definition. M of xy dx plus n of xy dy equals 0 is homogeneous if m and n are both homogeneous functions. Whoops. homogeneous functions of the same degree. So basically the functions m and n need to both be homogeneous of the same degree. Then you have a homogeneous differential equation. Now, how do we solve a homogeneous differential equation? So to solve, we make a substitution. We have two substitutions that we can make. We can make the first one, y equals u times x, and u becomes the new dependent variable. Or x equals v times y, where we treat y like the independent variable and x as the dependent variable. And this one would be v is the new dependent variable. So either of these substitutions will reduce the equation to a separable equation. So I usually pick one. I usually pick the first one. So I typically use y equals u times x, and this will always make the differential equation separable. So always make it separable. Now, let me go through something here, because I basically have to substitute everywhere I see a y in my differential equation. I'm going to put a u times x, but I also have to replace the differential dy. So let's look at the differential dy. So dy, let's say if y is equal to u of x times, u of x times x, then dy dx is d by dx of u of x times x, which is going to be a product rule. So it's going to be x times u prime of x plus derivative of x, which is 1 times u of x. And what is u prime? We could rewrite u prime as du dx. So that's just du dx. So we can rewrite it that way. And then we can say that dy dx, so dy dx is equal to x times du dx plus u. Now multiply through by dx, that's bad to say, but we can say dy equals x du plus u dx. So that's what we're going to substitute in for dy every time we use the substitution y equals u times x. So y equals u times x, dy equals x du plus u dx. We substitute all of that into the differential equation, and somehow magically, not magically, but I'm just not going over it, the differential equation will become separable. So let's look at an example of what happens when we do this. So example, so we have the differential equation x times dy dx equals y plus square root of x squared minus y squared for x greater than 0. So let's look at the differential form first. So x dy equals y plus square root of x squared minus y squared times dx. And then we'll say move the dy term over. So this will become y plus square root of x squared minus y squared dx minus x dy equals 0. So here's our m, here's our n. Now, is it homogeneous? So how do you test if it's homogeneous? M of tx comma ty, and then also do the same thing for n. If they are homogeneous of the same degree, then it's a homogeneous equation. So this is going to be ty plus the square root of t squared x squared minus t squared y squared, which is ty plus t square root of x squared minus y squared. Now that's equal to t times y plus square root of x squared minus y squared. N of tx ty equal to negative tx, which is t times negative x, which is t times n of xy. So they are both to the first power. So just note they are both homogeneous of the same degree. Therefore, the differential equation is exact. It's exact. So what we could do is make a substitution. So now, make the substitution. Make the substitution. Y equals u times x. And dy, we know, is going to be u dx plus x du. So make the substitution y equals u times x, then the differential will change as well. So this becomes x times dy. Well, sorry. Let me use the form that I have here, this differential form. So that's going to be ux plus square root of x squared minus u squared x squared dx minus x times u dx plus x du equals 0. So I'm just substituting everything into the differential equation right here, where it's in differential form, everything's on the left. Now, I distribute and try to find some cancellations, hopefully. So if we do the distribution here, we get ux dx plus square root of x squared times 1 minus u squared dx minus ux dx minus x squared du equals 0. And now I see, yeah, I have a cancellation here. Those two cancel. And I can move this over to the right-hand side, so I could say square root, well, let me just write it as x times square root of 1 minus u squared dx equals x squared du. All right. Now I can separate the variables. I can divide by x squared, I can divide by square root of 1 minus u squared. So that's 1 over x dx equals 1 over square root of 1 minus u squared du. And now integrate both sides. On the left, integrate with respect to x. On the right, integrate with respect to u. Natural log x, absolute value, equals, what's the antiderivative of 1 over square root of 1 minus u squared du? I need somebody to type it in the chat quickly without Googling it. So we integrate on the left, we integrate 1 over x. What's the integral on the right? Integral of 1 over square root of 1 minus u squared. It should be some function of u. That's right, it's going to be sine inverse or arc sine of u plus c. Arc sine of u plus c. Now, the last thing to do, well, we don't have initial condition. So what we do is we say, okay, what was u? if y is u times x, then that would tell us that u would equal y over x. So substitute that back in. Get natural log absolute value of x equals arc sine y over x plus c. Now, if we had initial condition, we could solve for c by plugging in the y and x values at the initial condition, but we don't have it, so it's an implicit solution. I'm definitely not going to try to solve for y. I'm just going to leave it as an implicit solution. No, it's all good. So, any questions? Any questions at all? I think we may just go ahead and stop here. We are moving very quickly because of the new format. It's easy for me to move too quickly. So I'll slow down. We'll stop here. Be done for the day, I think, unless you guys have any questions. If it's an implicit solution, then you don't explicitly find y as a function of x. You have like a function of x and y on the left and a constant or something on the right. It's basically like you're not solving for y explicitly in terms of x. And then we call it an implicit solution. So that's what it means to be implicit. Explicit is the opposite in that you actually do solve for y in terms of x exclusively. So basically, what I would need to do to solve for y is move the constant over. Kind of, yeah. Before integrating, I had to rearrange so that I could completely separate the variables. Because on the left, I want to integrate with respect to x, and on the right, I want to integrate with respect to u. So that's why I separated, or I rearranged before I integrated. So it's hard to say when this will be uploaded to Moodle, this video, because the videos I recorded yesterday are still processing. So this one may take a little while to process as well. Hopefully not, but it could take a day or longer to process on their Zoom server. So hopefully not that long, but we'll see. Let's see, it said, would you, oh yeah, so Brandon said, would you take the sine of the arc sine to solve? So basically, yeah, I would move the constant over. So basically, I would just say natural log plus c on the left, and then I would take the sine of both sides and then multiply by x, and it would get really a little tricky. And I'd have to be careful because I have to make sure x is not 0 and stuff like that, which it can't be for natural log anyway. But so now, yeah, Devin says, what's up with the test? So let me stop the recording so I can go ahead and start processing. I don't think this is necessary to record. I'm just going to go ahead and stop the recording.